So welcome everybody. So we have a pretty packed schedule. So what I like to ask, if you are the next speaker, please get mic'd up. And when you're done, please go back there so they can get the mic so we can have like the next speaker going through. We really don't have that much buffer in terms of time, but I think that would you prefer, like you will get more contents. So we have Gary from SiTime. And I think Gary doesn't need an intro. Everyone knows Gary, the oscillator guy. So with no further ado, Gary, the floor is yours.
Okay, thank you, everybody. Boy, the lights are really blinding. It's really hard to see anybody. So, let me go ahead and get started. So this talk is about how do we synchronize different nodes in a data center. And there's an oscillator involved in that synchronization. And so therefore, we have an oscillator workstream as part of OCP TAP. And the oscillator workstream is tasked with creating new classes of oscillators to help simplify adoption. So this talk will be a discussion about what we've been doing in the oscillator workstream, the future directions that we're going, and if anybody would like to join us, we'd love to have you participate. So just very high-level overview. Within the data center, there's different levels of, or different classes of oscillators. We have the grandmaster. Usually that's an atomic clock or sometimes an OCXO. Then we have transparent clocks, which is typically an XO. And then we have boundary clocks, which could be either an OCXO or TCXO, but it hasn't really penetrated the data center yet, so that's an area for future growth. And then finally, in the servers, we typically have a TCXO or an OCXO, usually an OCXO in data centers and a TCXO in telecom. So within the oscillator workstream, the problem is that when folks look at an oscillator datasheet, they don't typically understand how it translates into performance at the PTP layer. In other words, what is the time error that's provided by a particular oscillator? So the goal of the oscillator workstream is to classify oscillators to try to help people identify the performance level and be able to predict it and have predictable performance when it's used within the data center. The other issue people are running into in the industry is holdover. So holdover is a very complex topic. It sounds fairly simple. When you lose connection to an upstream oscillator, you rely upon the local oscillator to keep the accurate frequency and time and phase. And holdover measurements are usually performed differently by different companies. Even within the same company, they can be performed differently. So we want to provide a somewhat transparent way to measure holdover so that we can compare oscillators apples to apples. And so the goal of this workstream is to create oscillator classes for different use cases, but not only create the classes, but create the test methods to verify performance for each one of those classes. So the standardizing the test methods is an area that we're getting into now. When we started the workstream, there was many different use case scenarios. And the ones that we've started on so far are the ones that have been adopted to date, which is the grandmaster. Typically, this is satisfied by an atomic clock. And then we have the transparent clock and the ordinary clock. So these are the ones that we've focused on to date. But there's many other applications that are emerging. And so if you are working on one of these new upcoming applications or one that's not on this list, we'd love to hear from you to join our work to create classes for each of those applications. So the first class that we finalized in terms of the requirements is the grandmaster class in a typical, conventional data center environment. And this one we're calling class G1, G for grandmaster and 1 for the first one. And it's probably a little bit too hard for you to read the actual specs, but there's a document linked here. If you're interested, you can go look at it online. And it spells out the requirements for frequency stability over temperature, for G sensitivity, for aging, holdover, all the requirements necessary to operate in a standard data center environment without synchronous Ethernet. In the near term, we're going to be modifying that to include that document to include other oscillator classes. So this class is for a transparent clock, and these are the normative specs. So it has a G sensitivity spec, has a frequency stability all-inclusive spec, and we're asking that if there's any special design requirements the oscillator has to have, then the oscillator manufacturer will need to include what those are. That's for a transparent clock. There's another one for ordinary clock. It has very similar specifications. So these are the types of oscillators that are being used today in the data center environment. And if you have a niche application that would require something different, then that would be useful for you to bring into the oscillator workstream so we can work on it and create an open source class around it. So that's the classes. Now, once we have the classes created, they have a bunch of specs. Then we have to worry about how do we test to each one of those specifications. And so we've started a journey for the most complex, I guess the 5 most complex measurements. The first one is holdover. And last year we gave an extended talk on holdover here about the methodology that we're going to use. And we're still collecting data. When we have the data, we'll provide it and collect more feedback and standardize that. We've expanded that document to include frequency stability over temperature, which is a fairly straightforward measurement that people use, but often can get confusing how to do the measurement. So frequency stability over temperature, and then if you take the derivative of that, frequency stability over temperature slope, and then we have Allen deviation, which is a measure of random variation of the oscillator, and then holdover. So those are the 5 measurements that we're going to quantify test methods for. Each test method will have a normative and an informative section. The normative section would be requirements. So we have to converge on a standard definition, how we're going to measure it, and if there's any post-processing of the measurement data. The normative part of it is, this is the requirements you have to go through. And then the informative part is, this is an example of how somebody could do that. So it gives a lot more detail. The normative only goes through the very specific steps you have to do in order to have apples-to-apples comparison data. It doesn't spell out every detail, whereas the informative section does spell out quite significantly a lot of details, and I'll show you an example of that in a minute. So this, we'll call it the test setup, the test equipment, how do you prepare for the test, any special considerations you would have. We'd like to also provide pseudocode or even, I would say MATLAB or Octave code, because Octave is really the free version equivalent of MATLAB. And if we can provide code snippets of the core technical details, then that'll save the community a lot of time questioning about how do we actually implement it. So we'd like to definitely include some code snippets. And then finally, example data, so that people can actually see how the methodology gets applied to the raw data, gets post-processed, and ends up at the actual data. And then finally, it's really important to have references, because usually when I present at conferences, one of the first questions people ask is, do you check standard so-and-so, IEEE 1193 or 1139? So we definitely want to reference, we don't want to reinvent the wheel, we want to reference what other people have done and build on their learning. So we definitely want to have a references section. So this is just an illustration of the document. One of the engineers at SiTime, Gerald Tao, he's in our characterization group. He started and he's done a lot of detail here, and this document is available to anybody. So please let me know if you'd like to get access to that document. We continue to develop it every month for the new requirements. So this is just an example of a definition, how we define frequency stability over temperature. Has an equation Fmax plus Fmin divided by 2, gives an illustration. And then we have the test setup. So in this example, this is part of the informative section. So it's illustrating that you want to have your bypass capacitors connected up. You want to place it as close to VDD as possible. We recommend using a frequency counter. This is the way that we recommend to connect the frequency counter. You're going to require a more accurate reference. So if you're measuring a TCXO or an OCXO, you can use an atomic reference like was shown here for rubidium, and have it disciplined to GPS if necessary. The test equipment is also informative. So here we just spell out all the equipment that you would want to use in the previous test setup. And we provide example equipment for different manufacturers' equipment. If you're an instrument manufacturer, you want to have your product listed here, please let us know. This is meant to be agnostic as possible, but just to give people an idea of how you would set up the test with what equipment you could use. And then how do you prepare the device? I won't go into all the details, but we do provide a lot of details how to do that. Considerations, key considerations. So when you're measuring a particular device under test, you always want to, when you're measuring edges or time of a device under test, you always want to reference it to something that's more accurate. So the stability reference should be 2 orders of magnitude more accurate. So these are just common things within the industry and maybe not so common things, but we just want to spell everything out. How do we do the measurement step by step? Again, this is called out for each one. And if you're going to post-process the data, how do you do that? And then finally, references. So here in this particular standard, there's a lot of good stuff already published in IEEE 1193 that we're referencing and specific sections in that document. So this is the framework that we're going to use for the following 3 or 4 measurements that I listed in the beginning. And if anybody has an interest to contribute, that'd be great. So what about the future direction? What are the open questions? First of all, we have the test method, right? But how do we actually verify compliance? When I go in front of the incubation committee and I show them the documents that we have for the specifications, the first question is, how do we test for compliance? Well, now we'll have the test methodologies worked out, but can that be done by the clock and oscillator vendor? Should it be done by a third party like UNH IOL? Should it be an option in the test equipment, like a drop-down box from a Keysight frequency counter, or in the CalNex equipment, should we have an option in there to perform those testings? Each one of those has a different level of requirements in terms of like cost for the end user and maybe also trust, I suppose. So we'd like to get the community's feedback on what you would like to see there. And what are additional use cases? So data centers are fairly broad. We're looking at hyperscalers in the beginning, but there's many other applications when you go out to the edge, when you're looking at other niche applications for data centers that are in modular containers or shipping containers, where there's data centers literally docked out in the bay on a ship. So there's a lot of different applications for data centers, and we want to try to include as much as we can as people have an interest. So bring those into the oscillator workstream. We'd love to work on them. And holdover requirements. So a lot of, well, the oscillator vendors like to publish what their holdover requirements are, but within the data center, I don't think there's any particular, there's nothing that's been documented other than what we've done at OCP TAP. So if you're working in a data center environment and you have needs for holdover, please let us know what those requirements are so we can make sure they're accounted for in the work stream. So if you'd like to watch any of the past meetings that we've had, they all get recorded. They're all on linked at this link here for the wiki tap oscillators. If you want to attend future meetings, you don't have to sign up in anything. Just let me know. Send me an email. My email address is in the wiki page, so you can find it there. If you want to look at the oscillator class requirements, and as we update it, it'll still be available online to everybody. And if you want to, in general, join the OCP TAP mailing list, please do, and here's the link. So that's essentially in the presentation. Are there any questions?
Can you hear me? Yeah. Great. So floor is open for questions. 2 microphones. Maybe I can start with a question. People are shy. So the requirements for the data center, can you elaborate more, like what we so far have, like in terms of environmental things?
Yeah, I mean, typically, well, we have 3 requirements that I discussed: the Grandmaster, the transparent clock, and the ordinary clock. The Grandmaster clock, the requirements are typically satisfied by an atomic clock today. And we want to expand that into an OCXO for a POPs environment, the point of presence servers. Today, we just have the Grandmaster for the hyperscaler environment. It has G sensitivity requirements, so shock and vibration can be important. If we're working in an area and if it's an equipment rack, and even though the particular Grandmaster itself is being left alone, if there's equipment next to it and that gets removed or replaced, that can create shock that transfers through the chassis into the Grandmaster. There's also requirements for holdover, which is one of the more difficult ones, and holdover is a function of the thermal environment and the changing gradients. Typically, the data centers are pretty well controlled in terms of temperature, but there could be some gradient still from the HVAC system, or if there's a problem with the HVAC system, if that goes down. So those would be the main thermal environments.
Any more question?
Yes, I got. Thank you. Nice presentation and your test procedure. I was wondering, you just mentioned, of course, data centers are temperature controlled, but over what temperature range are you planning to test these various oscillators?
Sure. So if we go back and look at the temperature requirements here, they're the first rows. So in the Grandmaster, we're looking between -10 and 70 degrees C, and then also between 0 and 45 degrees C. So sort of the widest range that we'd expect to see in an environment in the data center, -10 to 70, and then the more typical environment, 0 to 45. And then that carries over to the other specs as well, -10 to 70. Yep.
Thank you.
Sure.
Any more question? I have another question. So, for the NICs, like you have constantly, let's say, servo running, what kind of specs you see they can improve, let's say, the performance of the servo, aside from like the transport, but on the like basically the follower, the ordinary clock in terms of specs?
So the question is, what are the specs you would want to see for an ordinary clock in a NIC? So the NICs are in the servers, and they're, servers, there's many, it's a high volume application. So you wouldn't want to see an atomic clock or a OCXO in there. And within a data center environment, typically it's just an XO is what we use. Eventually, if synchronous Ethernet makes its way into the data center, then it could switch to become a TCXO. But today we're seeing an XO, and typically the stability is what you're seeing here, 100 ppm. And that's all inclusive, so it includes aging effects, thermal drift, wander, and so on. So the specification today is fairly loose. That gets us down to about a 1 microsecond time error in a NIC card. As applications get developed and we have tighter requirements going below a microsecond, then you would need to bring in a TCXO. But we're waiting for applications in the software layer to take advantage of that, for operators to introduce services for time-sensitive applications. So typically, oscillators in a NIC, an XO, the largest source of error is going to be thermal drift, so temperature variation or temperature gradients. That's going to be the largest issue.
Thank you.
Question, is there a temperature gradient requirement as well that you're specifying, or bound on the ppm per second, for example?
That's a good question. Is there a temperature gradient requirement? Today there's not, because when we polled the community, we didn't get a requirement for it. There's an implicit requirement in the Grandmaster. So that one actually has holdover. And when you have holdover, the thermal drift is kind of implied in there. So there's a separate spec for frequency stability over temperature slope here in I guess the fifth line down, 7 parts per trillion per degree C. And that has a very specific thermal profile associated with it, with a thermal ramp rate and a soak time. And that's spelled out in the standard. I don't show it here, but it's actually the footnote 2. So that is well defined for the Grandmaster because that's super accurate application. When it comes to the class T1 or F1, the accuracy is sufficiently loose that, and we didn't get a requirement from the community, so we don't have anything specifically spelled out for that. But if you want to introduce that for a particular application, we'd love to hear from the community. Good question.
Thank you, Gary. Okay, next presenter.
All right, thank you.